It is a rare chemical equation where the reactants are in their stoichiometric perfect amounts. What I'm saying is they don't mutually run out at the same time. Usually one runs out before the other. And in true chemistry style, we have a term, a fancy term for that. The reactant that runs out is called the limiting reactant. It determines the amount of product that is made, because when the limiting reactant runs out, the reaction stops. The excess reactant is the reactant that's left over. So we also have a way to figure out the limiting and the excess reactant and how much product can be made by the limiting reactant using stoichiometry. Okay. If I have a statement that says 27 grams of hydrogen gas react with 15 grams of oxygen gas to form water, you need to figure out how much water is produced. But before you can do that, you have to figure out which one of these products will run out first. So this is how you do it. You write and balance the equation, and you do two separate dimensional analysis problems to show the amount of product that is formed. I start with my 27 grams of hydrogen. I multiply it by the molar mass of hydrogen to get moles of hydrogen. I do my stoichiometry step comparing the coefficients of the balanced equations. And then I take my mole of water, multiply, and relate it to its molar mass, and I figure out I can make 243 grams of water if I use up all of the hydrogen. The amount of water that I can make with 15 grams of oxygen, going through the dimensional analysis in stoichiometry, I find I can make 16.8 grams of water. 16.8 grams is all the water I can make, because at that point I have no more oxygen. I can't make water without oxygen, so the reaction stops. The limiting reactant is the oxygen. The excess reactant is the hydrogen. There will be hydrogen left over that is unreacted. Now, how do we know how much of the hydrogen we used to make our 16.8 grams of water? Use dimensional analysis to find out. So 16.8 grams of water, the amount of water that was made when we ran out of oxygen, when the reaction stopped, requires 1.87 grams of hydrogen. That means if I started out with 27 grams of hydrogen, I used 1.9, that's 1.87 rounded, 1.9 grams of hydrogen unreacted in my reaction chamber for 25.1 grams of leftover hydrogen. The theoretical yield is the maximum amount of product that can be made by a perfect chemist under perfect conditions in a perfect world. It really is just the calculated amount using the limited reactant. Here's a real world analogy for you. I'm sure most of you have made Toll House cookies. On the back of the Nestle's chocolate chip bag is a recipe for Toll House cookies. And it tells you you can make 3 dozen Toll House cookies from one recipe of Toll House cookie chips and the other ingredients. My guess, and that's the theoretical yield. It's how much you should be able to make because everything's perfect. I know you don't get 3 dozen cookies out of your one batch of Toll House cookies. My guess, it's about 2 dozen. What happens? You eat the cookie dough, don't do that because you could get salmonella. You make cookies that are weird size, you drop some on the floor, whatever. That is your actual yield. To find your percent yield, you take your actual yield, which is also the results of your experiment because you're not using cookie dough in class. You divide it by the theoretical yield, the amount you should get, and you base this from your stoichiometry, and you multiply the whole thing by 100. Okay, let's do some practice problems. The first problem says, determine the mass of P4O10 formed if 25 grams of phosphorus and 50 grams of oxygen are combined. What's the limiting reactant? How much excess reactant remains after the reaction stops? Here is a word of warning to you. Make sure the reaction is balanced, otherwise you will get the wrong answer and it'll be really annoying. So you have seen that you start up 25 grams of P4 and 50 grams of oxygen, and you need to figure out which one of these runs out, and when it runs out and stops the reaction, how much P4O10 is formed. So we do two side-by-side stoichiometry problems. The first one says how many grams of P4O10 can be obtained when 25 grams of P4 are reacted. So grams of P4 go on top, moles of P4 go on the bottom. The molar mass of 4 atoms of phosphorus bonded together is 124. My next step is my stoichiometry step that allows me to stop calculating P4 and start calculating P4O10. The moles of P4 go on the bottom because we always move in a diagonal fashion, and P4O10 goes on top. And now we're ready to calculate the grams of P4O10. And the molar mass of P4O10 is 284 grams. So when I use up all of my P4, I can make 57.3 grams of P4O10. The amount of P4O10 that can be formed from 50 grams of O2 is calculated in this fashion. The stoichiometry, the ratio of coefficients here is there are 5 O2s react to form 1 mole of P4O10. 1 mole of P4O10 still has a molar mass of 284. Using up all my oxygen will make will make 88.8 grams of P4O10. The limiting reactant is the P4. It runs out and it makes 57.3 grams of P4O10. They would like to know how much excess reactant, that would be O2, remains after the reaction stops. Clearly, there is some oxygen in the 57 grams of P4O10 that was formed. So of the 50 grams of oxygen that we started with, some of it is now bonded in with P to form P4O10. How much? Well, we can find that out with stoichiometry. We would like to know the number of grams of oxygen that were converted into 57.3 grams of P4O10. And this kind of looks like the same problem we did before, only backwards. 284 grams of P4O10 in 1 mole of P4O10. 1 mole of P4O10 is equal to 5 moles of oxygen, and 1 mole of oxygen has a molar mass of 32 grams. And in 57.3 grams of P4O10, there are 32.3 grams of O2 as a reactant that is unavailable. We started out with 50 grams of oxygen. 32.3 grams of that oxygen was used to form the P4O10. That means in our reaction chamber we have 17.7 grams of O2 that is unreacted. All right, one more problem. Nitrogen can be prepared by passing gaseous ammonia over solid copper to oxide at high temperatures. The other products of the reaction are solid copper and water vapor. Let's just write an equation really quick before we go any further. So NH3 reacts with copper 2 oxide to form N2, and the other products are solid copper in water. Oh, that's supposed to be in past. Okay. And when I balance, I come up with and they say we start out with 18.1 grams of NH3 and 90.4 grams of the copper 2 oxide, and they want to know how many grams of N2 are formed. I have to figure out which one is the limiting reactant. So the number of grams of N2 that can be formed by 18.1 grams of NH3 looks like this. Using my stoichiometry relationships, 2 moles of N3 result in 1 mole of N2, and 1 mole of N2 has a molar mass of 28 grams, and so I can make 14.9 grams of N2 when I use up all of the NH3. The amount of nitrogen that can be made with the 90.4 grams of copper 2 oxide depends on its molar mass, 79.5 grams of copper 2 oxide and 1 mole of copper 2 oxide. 3 moles of copper 2 oxide is equivalent to 1 mole of N2, and 1 mole of N2 has a molar mass of 28 grams, and I can make 10.6 grams of N2 using all of the copper 2 oxide. It runs out, so the total amount of N2 that can be made from the copper 2 oxide is 10.6 grams.